There we go. Okay. Can we see okay? Right, let's continue then. Dropbox, DIFC, workbook, physics, lecture, mechanics, kinetic and potential energy. Okay. Right. We can write this down. Kinetic and potential energy.
The deadline for Tuesday is Wednesday?
I thought we agreed Tuesday. Yeah, Tuesday 11 p.m. Yeah.
Is it the whole thing or just the 800?
No, just the 800 words with the 6 sources. Yeah. Oh, sorry. I left my bicycle outside. It's raining. Yeah, look at it. Terrible. Yeah.
So the storm is coming tonight.
It is indeed. Alright. Kinetic and potential energy. You got that? Yep. Do you remember which energy is kinetic? Which one's that? Moving, yeah. And potential? Well, yeah. Yeah. Alright. So, if an object's moving, then it has kinetic energy. And this energy is from some work being done on the object. That is, kinetic energy equals the work done to give it that energy. So what I'm saying is, if this guy is moving, it has kinetic energy. Where did it get the kinetic energy from? So imagine it's at rest, and now it's moving. It has kinetic energy. But this energy didn't just come from nowhere. Remember, conservation of energy? And thank you. So, for this to have kinetic energy, it means that something must have done work to it to give it the energy. Yeah? If a mass m is moving with speed v, then how much kinetic energy does it have? Let us see. Okay, so you'll need to write this down. I want to calculate the formula to work out kinetic energy. So this is how I imagine it. This is at rest. And this guy here, he pushes it and he does some work. Now, this is moving with V. So this kinetic energy, that must equal the work the person did to give it that energy. Make sense? Because it has to come from somewhere. So, the kinetic energy equals the work. And does anybody remember the formula for work? No, that's weight. Yeah, that's it. Force times distance. And what did Newton say force is? Mass times acceleration. Okay? Now the only problem is, okay, we know the m, but we don't know the a or the s. What do we know? We know the v, and we actually also know the u. So we don't really want an a and an s here, because we don't know a and s. But we do know v squared equals u squared plus 2as. Yeah? But what's u squared? 0. So a half v squared is equal to as, if I divide by 2. So if I put that formula in there for as, so this as here, I replace it with a half v squared, I get the formula, a half v squared. So that's it. The kinetic energy is equal to, excuse me, oh come on, a half mv squared. That's the formula for kinetic energy. And in fact, I would hope that some of you have seen this formula before. Yeah? So this is where the formula comes from. Okie dokie, got that? Got that, guys? Not yet there. So what happens if the mass is bigger? Well, then it has more kinetic energy. What happens if the velocity is bigger? Then it has more kinetic energy. But which matters more, the m or the v? Which is more important?
V?
Yeah, why is that? Like, what makes the v more important in the formula?
It should be bigger than the mass, so it's not
Why bigger?
square.
Yeah, the squared, yeah. See, because the v is squared. So if you make the mass twice as big, what happens to the energy? Well, it's twice as big. But if you make the speed twice as big, what happens to the energy? It's 4 times bigger, because it's 2 squared. Okay, so the kinetic energy is the energy due to the movement, and the faster it moves, the more energy it has. All right, is that okay? Can we continue? Yeah. Okay. So that's kinetic. So obviously now the next one is potential. So if an object is at a height h above the ground, then it will have potential energy stored in it. It got this energy because someone did work on it. That is, a force brought it to that height. So just like the kinetic, the potential energy is the work done. So anyways, let me explain more. So if I hold this here, it has energy because it can do work. It could fall and break something. Okay? It has this energy because it's here. But how did it get here? How did it get up here?
You lifted
I lifted it up, yeah. So the energy taken from my arm to lift it should equal how much energy it now has inside, stored. Okay, so energy from my arm has now gone into this. Okay, so let's calculate now how much energy that is. So back to our arm. So here it is, it's on the ground. It has no energy. And then somebody lifts it up, and maybe they put it on the top of it, a shelf up here. Okay, so now this has energy in it because it can be released by dropping it. You know, just give it a little push and down it goes. Well, let's just call this height here h. Okay, so what's the potential energy? Potential energy will equal the force by the distance. Now, here's the thing. What is the force here? So as he's moving this up, there's 2 forces. The weight, which is mg, and his force, which is F. If he wants to move this, how big should F be? What should F equal?
mg.
Should equal mg, yeah. So F is mg. And what is the S that he moves it? What's the distance here? H. And there you go. That's the formula for potential energy. Potential energy is mgh. Got that? Yep. Easier to prove. Okay, continue. Yeah? So, next. Something important about potential energy I want to say. So, if we go back to our formula for kinetic energy, a half is positive. The m, positive. The v squared, positive. So the kinetic energy can only be positive. I think we can all see that. But the potential energy is a little bit interesting. Because the potential energy could be negative. Because the h, remember, was really an s. And s is displacement. So it could be positive, or if it's underneath, it could be negative. So anyway, the potential energy has three different meanings depending on if it's positive, zero, or negative. So if the potential energy is positive, then that simply means it has potential energy, and that's all. If the potential energy is zero, that means we say the object is free. So what do I mean by that? Well, let me draw a picture here. So here is somebody fallen. So they have a potential energy which is positive because they can do some work. This guy here who's on the ground, his potential energy is zero, and we call that free, meaning he can move left and he can move right, and this guy here, he's not really free. He's kind of releasing his potential energy by falling. Okay, well, this guy is free. And the last one is negative. What way would I draw my picture to make the man have a negative potential? Yeah. So here he's negative, so the potential energy is negative. How would you describe his situation? It's the bottom of a hole. How would you describe his situation?
Can't really do anything.
Yeah, so what word would describe his situation?
Stuck.
Yeah, another word for stuck. Give me a synonym for stuck.
Can't move.
Yeah, one word.
Trapped.
Trapped. Trapped. Yeah. If it's negative, we say he's trapped in a potential well. So the reason we say he's trapped is because if he wants to be free, like his friend, he has to spend energy to get out, to be free like him. Okay? So negative potential energy, we say that the person is trapped in what we call a potential well, like a potential hole. Oh, the rain. Oh, goodness sake.
What does potential well mean?
Potential well means like potential hole, that you're at the bottom of something and you're stuck in there and you need energy to get out. You know a well in English, like where you get the water from? Water from the bottom of a well.
Mm-hmm.
Okay, is that okay?
But then wouldn't it go back to being positive because he's doing good?
Well, his potential energy will go to zero because he's doing work. He's cancelling the negative energy. Yeah.
Potential energy only off vertical.
No, just the potential energy we're looking at right now is only vertical, but we'll discover that, really can have many types of potential energy in many directions. But we're just looking at the vertical because it's caused by gravity. Okay, we got this? Yeah? You continue? Okay, so, whoops. The conservation of energy means that all the kinetic and potential energy at the beginning should equal the total kinetic and potential energy at the end. So as a formula, you can say it like as this: energy at the start equals energy at the end. So kinetic plus potential at the start equals kinetic plus potential at the end. Now, there is one condition. This is for an isolated system. Before you write that down, I'll just show you what I mean. So, like, if you have a box here, and imagine you have a ball in it, so the ball is bouncing around. So, its potential energy is changing because its height's getting smaller. Yeah? So what do you think must be happening to its kinetic energy as it's going down? It's getting bigger or smaller? Now remember, the potential energy is getting smaller. Bigger, yeah. But why?
They're inversely proportional.
Because the energy is conserved. So the energy, which is the kinetic plus potential, doesn't change. It has to be equal, yeah. So if the potential energy is decreasing, then the kinetic energy must be increasing, so that this stays constant. Okay. But this is not true if all of a sudden if I put this under a fire and put heat into it. And the reason for that is because I'm putting energy in from the outside world. So this is what I mean when I say this only works if the system is isolated. You don't have some outside interference. Okay. This is the conservation of energy for today in the formula. You can write this down. Yeah. In physics, we imagine most systems are isolated. In real life, no system is isolated. So you might think this room is isolated, but when you think about it, there's energy coming in and out of the room. You know, heat energy is going out sometimes, heat energy is coming in sometimes. It's not quite isolated. Okay, continue. Yeah? So let's have a look at an example. I think we can do this one together. So a 1 kilogram ball is dropped from 10 meters. Using your formula, tell me what potential energy it has, please. Yeah, I'll open up the calculator for this. So it's m times g times h. So it's 1 times 9.81 times 10. So that's 98.1 joules of energy. 98.1. Okay, did you write that down? 98.1. Right. How much kinetic energy does it have initially? So at the beginning, how much kinetic energy does it have? Yeah, which? One of those answers is right, but which one?
0.
Correct. Why?
Because it's not moving?
Yeah. At the beginning it's at rest, so it has no kinetic energy.
V is 0.
Yeah, the V is 0. So 0 joules is the answer for part B. You can write that down, 0 joules. How much potential energy does it have at the moment of impact? So just when it hits the ground, how much potential energy does it have? What do we think?
0.
Why?
Because the height is 0.
Yeah. So 0 joules for part C. lastly, how much kinetic energy does it have when it hits the ground? What do you think? Or how could we do this? Not zero. 'Cause, what I mean, just right before it hits the ground, so it's still moving, just like right at the moment before it impacts. What's the kinetic energy?
98.1.
Correct, yeah. Now why?
Because the force,
Yeah.
when before the ball hits the ground,
Mhm.
you still have energy as force.
Mhm. Yeah. So the energy before it hits the what he's saying is the energy before it hits the ground, it should still equal the energy it had earlier. How much energy did it have at the beginning? Well, it had at the beginning here, kinetic potential. What did we say the kinetic was at the beginning? 0 joules. And the potential? 98.1 joules. So the total at the beginning, 98.1 joules. Okay. Now when it hits the ground, what's the kinetic? We don't know. What's the potential? 0. What should the total be? It's supposed to be 98.1 joules. Therefore, the only possibility is the kinetic energy at the end is also 98.1 joules. And if you don't believe me, what you could always do is UVATS, calculate the V, and do a half mv squared. And you'll get the same answer. Is this okay, guys? It makes sense? Kim, is it okay? I know it's okay for you, Chow, because you gave me the answer. George?
Now can we just say that all the potential energy?
Yeah, all the potential energy has
Well,
become kinetic energy.
Yeah.
Yeah. Okay, continue. Okay, so here's another one. A 200-gram bullet is fired horizontally from a height of 10 meters at 100 meters per second. How fast is it going when it hits the ground? Let me draw that for you. So the bullet is like here. That's a bullet. And it's 200 grams, and it's fired out at 100 meters per second, and the height here is 10 meters. So what'll happen is it'll go like this. Crash. This should remind you of a question we did in projectiles. Do you remember this one in projectiles? So, what if we were doing this in projectiles? First, we would have to get what? What would we have to do first?
Find the angle.
Yeah. Do you know what, actually? Would you like me to do this one as a projectile question, as a bit of revision? So I could just do this the way we did it in projectiles, so you can have a little bit of a revision.
But can you also do the...
Of course, we'll do it both ways. I want to show you you'll get the same answer. Okay? So, if we were doing this as projectiles, let's look at the vertical first, the Y. Okay, so what's the U, what's the V, what's the A, what's the T, and what's the S? Okay, so vertically, what's the U?
Zero.
Sure, very good. And the V? We don't know. And the A? Minus G. And the T? Don't know. And the, be careful. And the S? Yeah. What is it? Nearly minus 10.
Because it's above
It goes down 10 meters. Yeah? Okay. So what would be the formula that gives me the V? Which formula should I use? V squared maybe? V squared equals U squared plus 2AS. So I'll get V squared equals 196.2 in total. So V would be the square root of this, please. What's that?
14.007.
14.007.
Seven.
Okay, so about 14.
0.0.
So it's about 14 meters per second. Yeah. Okay? Now, I now have just worked out that when it hits the ground, it's going, oh, actually, this is minus 14, because remember in maths when you have this equation, you could have a plus or a minus. Now, why did I choose the minus and not the plus? Yeah, because I know it should be going down here with 14. Now, who knows how fast it's going horizontally? So if we look in the x direction, we have our triangle. What's the distance? We don't know. What's the speed? In the horizontal?
100 meters.
100. And what's the time? We don't know. But that's okay, because the only thing I need to know is the speed. And what is the speed in the x? 100. Just remind me, why is the speed 100 here and also 100 at the beginning in the x? Why does the speed not change in the x? Yeah, the gravity only acts on the y. So the speeds in the x don't change. Okay? So, here is my velocity. I have 100 this way and 14 this way. How do I get the speed? Not cost, yeah, you're thinking of resolving. I want the magnitude. The square root of, yeah, 100 squared plus 14 squared. So what on earth is that, please? $100.97. 100.97, so 101 then, joules. Okay, so write this down and then I'll do it the other way now. Yeah, why is it joules? It's not. It should be 101 meters per second. It's a speed. Yeah. Okay. Got that? Got that? Not yet? Okay. So in a moment we'll recalculate this using energy. Okay? So, let's do this again. Right, when the bullet is here, what types of energy does it have? So I'll write energy 1. Okay, does it have potential? Yeah, because it's, what's it, 10? How many meters did I say here? 10, was it? 10. So the formula is mg. Oh, sorry, that's not the M. Sorry, what's the M here? Yeah, mg h. Okay. Does it have kinetic at the beginning? In this case, it does. You just fired the bullet. So, it's a half m, and what's the speed at the beginning? 100. 100 squared. Okay. Can someone hit that in, please? We'll get this. One oh one nine six two joules. Yeah. Now let's look at the energy at the end. Does it have potential when it hits the ground? 0. Does it have kinetic? Of course it does. It's a half, and the V we don't know. That's the thing we want. So according to conservation of energy, E1 should equal E2. So that means 1019.62 should equal 0.1 V squared, because a half of 0.2 is 0.1. So I'll just divide by 0.1. And then I'll take the square root. This number seems too big. Is it exactly the same? Wonderful. Okay. And then you take the square root. So, square root. So therefore, 101 meters per second. Same answer. Same answer. Okay. Continue? Yes? Yes? Okay. So let's see. A block is placed at the top of a wedge 30 degrees inclined, and the longest face is 2 meters. How fast the block going when it reaches the bottom of the wedge? So let's have a look here. I'll draw the picture. Here's my picture. I have a wedge, and this side is 2 meters long, and this angle here is 30, and I put a mass here at rest, and then of course it slides down, and my question is, how fast is it going here, V? So let's use our energy, okay? So let's look at the energy at the top. So what type of energy does it have at the top? Kinetic, potential, or both? Oh, great, all 3 answers, wonderful. So, potential was the answer, because it's at rest at the beginning. Okay, it has only potential. So the formula for potential is M. Do we know M? No. G. Do we know G? Yes. And H. Do we know H? No, but we can work it out by resolving. So if this is 2 meters hypotenuse and this is 30 degrees, how big is this side? Ah, you guessed the wrong way. It's the other one. It's 2, which is this one? Cos 30. And this side? 2 sin 30.
One's trying to hide, so it's supposed to be sine.
Yeah, but I was asking for both, but you're right. This one is sine then, okay. 2 sin 30. Is 2 sin 30 1?
Yeah.
Right, so this will be equal to 9.81 m, because we don't know the m. Yeah? Now let's look at the bottom. When it hits the ground, what energy does it have? Kinetic, potential, or both?
Kinetic.
You went the wrong way this time. What is it?
Kinetic.
It has only kinetic, because there's no height. Which is a half m, which we don't know, v squared, which we don't know. But what we do know is that they should be equal. So 9.81 m should equal a half m v squared. Now what can I cancel here? M's. I should bring up this 2 to the left. So I get 19.62 equals v squared. So v is the square root of 19.62, which is 4.43 meters per second. Yep. Yep. Okay. So actually, yeah, no, that was it for that. So I'll give you a couple of minutes to try some of these. You're just using 2 formulas today, a half mv squared and mgh. Yeah. Now you can borrow this one here, Matt. That's okay. Sure, I'm not going to be doing any questions. I did these already when I made the book, so don't need to do them again.
Now, let's say in summative exams,
Mm-hmm.
will it be fine to bring in formulas with us?
I'll give you a formula book.
Oh.
Yeah.